Now we're going to move into chapter 7, and we're going to be talking about the central limit theorem. So when we talk about the central limit theorem, we are no longer dealing with individual values. We are now going to be dealing with sample means. And so the shape of the distribution of the sample means becomes approximately normal as the size of n, as the sample size n increases. So in other words, as you're taking those sample means, so you're finding your samples and you're finding a whole bunch of samples and you're putting together a distribution made up of those samples, as the sample size n increases, regardless of the shape of the population, the overall distribution will become approximately normal. So that's what we're going to be focusing in on today in section 7.1, and that is the sample means. The size of the sample n that is required in order to be large enough, quote unquote large enough, depends on the original population from which the samples are drawn. We say that the sample size should be at least 30. So we need an n value greater than or equal to 30, or the data, if it comes from a normal distribution, then we don't have to worry about that, that requirement that it's greater than 30, greater than or equal to 30. If the original population is far from normal, so if it's really a bizarre shape, then possibly more observations are needed. But our rule of thumb here is at least, as long as you have at least 30, you're safe. Or if your original population is normal, you're safe to use this central limit theorem as well. So now officially section 7.1, the central limit theorem for sample means, which remember those are averages. The sampling distribution of a statistic is a probability distribution for all the possible values of the statistic computed from a sample of size n. Okay, so that's stuff we've done in the past. But now the sampling distribution of the sample mean, which is x bar, I maybe should put that in parentheses here or commas around it, is the probability distribution of all the possible values of the random variable computed from a sample of size n from a population with mean mu and standard deviation sigma. So now we're going to be dealing with not just individual values. Again, like I mentioned, we're going to be dealing with sample means, and some unique things happen when we deal with sample means. Suppose x is a random variable with a distribution that may be known or unknown. It can be any distribution. Using subscripts that match the random variables, this shouldn't really say suppose, this is just our notation. Mu sub x means the mean of x, and sigma sub x means the standard deviation of x. So those are just our notations that we've used in the past. Since we've only kind of been dealing with one thing at a time, we just use mu and sigma, but now we're going to specify that this is talking about the mu of x, mu sub x, and sigma sub x. If there are random samples of size n, then as n increases, the random variable, the sample of x, the sample means of x, which consists of sample means, tends to be normally distributed. And so here's our notation. The sample means of x are part of this normal distribution where the mean is the same as the mean of the original population, but the standard deviation would be, in fact, here, let me make a note of this. Let me put in an extra step here. So I'm going to write this in a slightly different way. So x bar, and then we've got this, and then the way we would write this notationally is mu sub x bar and sigma sub x bar. Okay, and then we're defining what those things are. Well, notice that the mu of x bar is going to be the same as mu of the original population x. The standard deviation, however, is different. So the standard deviation of x bar is going to be the standard deviation of the original population divided by the square root of n. So that standard deviation is going to become smaller. The standard deviation is also called the standard error of the mean. And that means it's the standard deviation of the sampling distribution of that sample mean. So that's the part that really is going to be the key, is that the standard deviation of our sample mean differs from the standard deviation of the original data values. Suppose that the mean time for an oil change at a 10-minute oil change joint is $11.4 minutes, with a standard deviation of 3.2 minutes. Write the distribution x bar, part of the normal distribution given there. So what we would have is, we know x bar is part of the normal distribution. We know the mean doesn't change, so our mean is still going to be 11.4, comma, but then to find our new standard deviation, here's how we do it. Sigma sub x bar equals, and we would have the original standard deviation, which is 3.2 minutes, divided by the square root of n, and we don't actually know what n is yet, so that's about all we can do at this point. We'll just put 3.2 over the square root of n, and once they give us an n value, then we'll be able to put that in. For part B, we've still got this same situation, but if a random sample of 35 oil changes is selected, describe the sampling distribution of the sample mean. So we've got everything laid out here already. We're just going to be able to add this one extra piece of 35. So we'll take the square root of 35. So we're going to write x bar, part of the normal distribution, and our mean is 11.4. And our standard deviation on our calculators, we're just going to take 3.2 divided by the square root of 35. And that will give us 0.54. I'm going to go 09. I'm going to go with 4 decimal places there, just to be on the safe side, because what happens is, you can see these standard deviation of the original, and when we compare that to the standard deviation of the sample means, the standard deviation of the sample means is going to be much, much smaller. So that's going to affect our shape of our distribution. Now looking at part C, if a random sample of n equals 35 oil changes is selected, what is the probability that the mean oil change is less than 11 minutes? So what I'm going to do is, we can actually erase the original values that we had written here. We're going to use the updated values that we have with that n equaling 35, and we will draw a quick picture here so we can see what's going on. And we're going to have 11 minutes. Well, notice the mean is 11.4, and we want to know, what are the chances that we're going to get less than 11. So writing this down in probability form, what is the probability that a sample mean of 35, we already know that, is going to be less than 11 minutes? And we're going to use this, and with the information we've got there, we're going to type this into our calculators. So let me pull up the calculator. So now that we've got our calculator set up here, we're going to go to second, variables, to normal CDF. And since we want less than, oh, my values disappeared though, but we're looking for the probability that x bar is less than 11. So we're going to use a lower boundary of that -1 E99. Our upper boundary is going to be 11. The mu value is the 11.4, and the standard deviation is 0.5409. And then it's going to paste it in there for us, and we're going to hit enter, and it's going to find our value. So there is a, we'll say 0.23. Your probability is 0.23 of having a sample of n equals 35 oil changes being selected, and the time takes less than 11 minutes. For example 7.2, the length of time taken on the SAT for a group of students is normally distributed with a mean of 2.5 hours and a standard deviation of 0.25 hours. A sample size of n equals 60 is drawn randomly from the population. Find the probability that the sample mean is between 2 hours and 3 hours. Okay, so again, you have to key in on the fact that we're dealing with the sample mean. So here's our distribution information for the sample mean. it's going to be normal because it's bigger than 30, right? We're looking for n greater than 30. On the previous one, I should have mentioned that also. It was greater than 30. It was 35. Here it's 60. Our mean is going to be 2.5. And then our standard deviation, remember how we get that? That's going to be 0.25 divided by the square root of n, which is 60. So 0.25 divided by the square root of 60. And that gives us 0.0323. I'm going to go with 0.0323. And now we're going to find the probability that x bar is between 2 and 3 hours. So, all right, that's what we're looking at, probability between 2 and 3 hours. So we're going to go back to second variables, go down to CDF, normal CDF. And this time our lower boundary is the 2, and our upper boundary is the 3. We've got to put in our population mean, 2.5. And our standard deviation, so for the means, so 0.0323. And then hit enter, and that pastes it, and then we get it 1. So we have a chance of 1. Now, 1 is guaranteed. So a lot of times what we'll do, just so, since this has come up, a lot of times we'll put 0.9999. Okay, I don't know why I rounded off to 2 decimal places last time, but usually we use 4, so we'll use 0.9999, and that means it's really, really, really certain, but not quite. It's really, really likely, I should say, but not quite certain. So, and the reason, if you think about that, the reason is that if you think about how many standard deviations away, you're like 30 standard deviations either direction to get, or sorry, not 30. What do we have here? So 0.5 divided by 0.0323. You're 15 standard deviations in either direction. And remember, 3 standard deviations in either direction is already 99.7. So it seems reasonable that this would be 99.99% of the values, or of the chance that the sample mean will be in that range. Example 7.3, in a recent study reported in October, in a recent study reported on October 29th, 2012 on the Flurry blog, the mean age of tablet users is 34 years. Suppose the standard deviation is 15 years, take a sample size of 10. So again, with that information, it's greater than 30. We know it's going to be a normal distribution. We're going to be dealing with the sample mean here. So what are the mean and standard deviation for the sample mean ages? Well, mu of the sample mean is the same as mu of x. So for us, that is going to be, what did it say, 34. Then sigma, standard deviation of the sample mean, is equal to standard deviation of x over the square root of n, which in our case is 100. And so we know that that is, actually, let me write that out. That's the formula part. So we're going to have 15 divided by square root of 100. Square root of 100 is 10, so this ends up being 1.5. So those are the two values. If we want to write this out, x bar is going to be part of a normal distribution where the sample mean is 35 and the standard deviation or standard error is 1.5. Part B asks what the distribution looks like. Well, we've just figured out those values. We know that 35 goes in the middle. And then we're going to add 1.5 as we go standard deviations away. So this would be 36.5, 38, and 39.5. In the other direction, we'd have 33.5, 32, and 30.5. So that would be our distribution. Again, because there's over 30, the sample size is over 30, we know it's a normal distribution, and those would be our standard deviation above and below the mean values. Part C, find the probability that the sample mean, and again, I really want to stress this, we're doing something different than in Chapter 6. The sample mean age is more than 32 years. So we're looking for the probability that the sample mean age is greater than 32 and which is the reported mean of tablet users in a more recent study. So again, now we can go ahead and do our second variables. We're going to go to normal CDF. This time our lower boundary is the 32, and if we want to draw a picture here, that might be a good option. I had the picture on the previous slide, but our 35 was in the middle. Here's your 32 over here somewhere, and we're trying to find this area here. So again, picturing it, we would expect that to be a pretty large number, especially if you go back and look at the actual values we had for the standard deviations. I think we were probably 2 standard deviations below the mean there or something along those lines. So our lower boundary is the 32. Our upper boundary, remember we put in the 1E99. The mean of the distribution is 35, and then the standard deviation is 1.5. And we'll paste that, and we'll put in our answer, and we get 0.9772. 0.9772 when we round that off, and that would be our probability that x is greater than 32 for this sample mean. For part D, find the 95th percentile for the sample mean age. So again, sample mean age, but this time they're giving us the percentile. We have to find the value, the x mean value that goes with it, x bar value that goes with it. So remember, here's our 35. 95% we know is going to be pretty much way over here. And we're looking for 95th percentile means 95%, 0.95 is below this particular x bar value. So the idea here is we're looking for the probability that, what do we want to say here? X bar is less than C, let's say. I'm going to change my picture a little bit, and that's going to equal 0.95. So this is actually going to be a C value. So we're looking for the C value that would make this work out, and so that's where we use our inverse normal. So second variables, we go down to number 3, inverse normal, and our area this time is the 0.95. The sigma value is still 35, and the standard deviation value is still 1.5. And we paste it and hit enter, and we find out 37 point, probably 5, because this is years, we can probably round it up there. 37.5 years old is the number where 95% of the sample means would be below that 37.5 if we were taking samples of size 100. So that finishes up section 7.1. We've got 6 graded problems there. Again, the key difference between what we did in chapter 6 and what we're doing now in chapter 7 is in chapter 6, we were looking at the probability that individual values were, we'll say less than something, let's just say less than 10. And then we would get a number. Here, we're looking for the chances that sample mean values are less than some number, we'll say less than 10. And so the big thing that's the difference here is, notice the mu of x is equal to mu of x bar, so those are not going to change. That doesn't make any difference. But sigma of x bar, we have to make that adjustment. That's going to be sigma sub mu divided by the square root of n. So this becomes the important thing in our problems, because that is going to change the standard deviation. It's going to shrink the standard deviation and make everything smaller and closer to the mean, because that's what happens when you deal with averages. When you take the average of a large group, you kind of find the middle. So if you're finding a whole bunch of averages, you're only finding the middles all the time, and so it bunches everything closer and closer to that middle, to that mean. So that's going to be the key difference for us today in section 7.1.